So today we are going to learn how to draw shear and bending moment diagrams. So this is a given beam cantilever from fixed at this end, free at this end. That's a cantilever beam. We have two concentrated loads, 20 kilonewton and 40 kilonewton, and we have a total span of 6 meters. So we are required to draw shear and moment diagrams. Today we will go through, in the first session, we will go through the basic method of drawing shear and bending moment diagrams, which is by developing equations by considering cut sections in different segments of the beam. For example, the first step in this case would be to draw to draw free body diagram of the entire beam. So if this is the span of the beam, draw free body diagram of the entire beam. So let's draw the entire beam. So we will draw these forces, 20 kilonewton and then 40 kilonewton, and then we have a fixed support on this side. So we must show there are three possible directions that can develop, RA and MA, and that third one is this one. Although since we have no applied load in horizontal direction, this will be 0, and that's why I'm not showing it up over here. If there is a horizontal load, this can develop. Otherwise, right now this is 0. So let's show the distances, 3 meters and 3 meters. Now you need to apply simple equilibrium equations. Maybe you can start with summation Fy equal to 0, taking upward positive, and you made it Ra minus 20 minus 40 equal to 0, and this makes Ra equal to 60 kilonewton upward. This is a simple process. Next is summation of moment about, let's say, at point A equal to 0, and maybe you can treat this side positive, so you can say now MA can be solved over here equal to, now this is with a positive sign, it means it is in the same direction as shown on the free body diagram. This is the direction on the. So next is to consider a cutting plane. Maybe this is A, let's say A, B and C. Now if we consider a cutting plane through the beam between A and B, so we can draw a cutting plane somewhere over here, and we can draw next free body diagram of either the left segment or the right segment. So if you can see, these are the two segments that are formed. This is the left segment, and maybe this is, this is the right segment. So we can consider either of these segments. You can see this, the other one is a red segment. So let me draw the left segment. So I'm going to draw the left segment, free body diagram for the left segment. Now these are the reaction forces, 60 kilonewton, and this is 300 kilonewton meter. Now let's say this section was considered, cutting plane was considered at distance x from end A. So this distance would be at distance, this would be at distance x. Now we need to show a shear force and a bending moment over here. Since there are no horizontal loading in this case, so there is no axial force, but we have to show shear and bending moment on this section. Okay, so we have Vx and Mx. Next is to solve for a Vx and Mx by maybe using equilibrium equations. So let's consider equilibrium equations. Summation. Let's consider, let me label the names. This is A, and let's say this is X. This point is, let's say, X. Now let's consider summation of vertical, summation of moments first. Let's say summation M about X is equal to 0, and let's consider this direction positive. Then minus 300 kilonewton meter, this moment will be with the negative sign because we have considered for this equation this direction positive. Is it in the same direction? Yeah, it is in the same direction, sorry. So it is supposed to be
It's same direction.
this direction, so it is positive. And then 60 into x, 60 into its distance x, 60 into distance x. Whether it needs to be positive or negative, you need to see its direction. This is in this way. So naturally it is in the direction opposite to our positive, so it will be with a negative sign. What next? How about Vx? How about this force? Does it produce any moment about x? It is passing through x. I just shown it over here, but it is actually applied at this point. Passing through x. So what do you think? Does it produce any moment about x?
It's an internal force, or it's acting on a surface, so I don't think so. It won't produce any moment.
Yeah, the reason for it doesn't produce any moment about x, and the reason for that it is passing through x. It has zero lever arm. What about this one? What about this term? What next? Plus mx. Mx means m as a function of x. All right, m as a function of x, not m multiplied by x. All right. This is 60 times x, 60 multiplied by x, but this is just to say that m is a function of x equal to 0. So now mx is equal to what next? Summation of vertical forces. Summation of forces along y direction, treating upward positive. So we will write 60 because 60 is upward, so we treat upward positive, so that's why it is positive kilonewton. What next? What next? Yes, please. What next?
It's a Vx, sir, plus Vx.
Plus Vx. V as a function of x equal to 0. So you can solve this for Vx and say that Vx is equal to minus 60 kilonewton. Alright, so we have this equation for shear force. Now we have the equations for shear force and we have the equation for bending moment in terms of x, and we have considered section between A and B. So we can say that these two equations of V and M, they are valid only for x ranging between 0 and 3. Maybe I can say between 0 and 3 with 0 included but 3 not included. Or if you want to say, for this case, you can say 0 and 3 both are included, but in this case 0 is included but 3 is not, because we have cut the section. Better to say like this, for both of them. Alright, x 0 and 3. Alright, so both of these equations are valid for values of x between 0 and just short of 3, maybe up to 2.99999. Alright, meters. What next? We need to consider a section between B and C. Alright, between B and C. So let's redraw this. And this time consider section between B and C. Somewhere over here. Now x has this origin at the same point as we selected before, A. A is the origin for x. So this is x. Now so let's draw free body diagram again for the left segment. Maybe I can just copy the same and use it. Alright, so you can see so we need to show again our positive shear and positive bending moment. Again, this is a positive phase, so shear force will be directed upward for this case, positive shear. And then the positive bending moment will be again directed this way. So now again you have to follow the same procedure by considering equilibrium equations. I know you have done these processes in your mechanics of material course, but I just want to make sure that nobody misses on them, although not many people are attending this class, but I would like to make sure that you all those who are attending are making full benefit of it. So summation of moment about, let's say again same point, A equal to 0. No, let's say consider it about maybe you could call this point as y, maybe this point, summation of point about y equal to 0. So again let's treat this direction positive, so maybe you can write minus 300, sorry, plus 300 minus 60 x okay, let me change this. I would like to show this one positive. Alright, don't mind this, but I would like to do this. So RA, or should I say 60 times x is positive, and what next? Minus 300 what about 20? Minus 20 times its lever arm. Now its lever arm is given by this distance, and this distance is how much? X minus 3. This total is x, so if you take out this 3 you will get x minus 3. Alright. So this becomes 20 times x minus 3. Now again Vx will make no moment about y, and then we just have to write mx, so minus mx equal to 0. The reason I preferred this choice of positive sign was that in this way this will come with a negative sign, it means that I would just take this side, this one, to the other side to make it plus mx, and this itself will become, it will be easy to keep this on the same side and take just one term on the other side. So you need to change the sign of only one term by taking it to the other side and keep the rest of the equation intact. Just a matter of what seems convenient to you. Alright, just a matter of convenience, whatever you like. You could take it the other way around. So mx is equal to 60x minus 300 minus 20x plus 60. So this becomes 40x minus 240. That's right. mx. Similarly, if you consider summation of vertical forces and taking upward positive, you can write 60 kilonewton minus 20 kilonewton plus Vx equal to 0. Now Vx would become minus 40 kilonewton. Alright, so Vx equal to minus 40 kilonewton. Now we have two equations. Let me just highlight them. This equation and this equation. Now for both of these equations, we must make sure that these are valid for certain range of x values. So these are valid for x between 3 and 6 meters, 3 meters and 6 meters. These two are valid for this range of x values. All right. Now the next.
Excuse me, sir.
GG.
Sir, why did this 3 is not included in that x range?
Yeah, this 3 is included. If strictly speaking, this 3 is included for the bending moment equation because that is continuous. For that bending moment equation is continuous, but it is not included for this one because we have considered this time section between B and C. This exact point passing through exact B point is not included. For shear, you need to decide whether this 20 kilonewton load is a part of your segment or it is not a part of your segment. So if it is not a part of your segment, you're cutting just before this 20 kilonewton, somewhere just between, anywhere on this side, on the left side of B, your cutting plane is passing somewhere on the left of B, and if it is on the other side, it includes 20 kilonewton. So in fact, the reason we do not have to consider it is that if I give you some body like this, all right, and I ask you to maybe apply some forces like this, okay, something like this. Now it is only this part is where shearing can take place, because if you draw a shear force diagram, you will see that the shear force is, let me show you how the shear force diagram would look like. It would look like this, 0, then this way, and then it will go constant for this amount of length, and then it will change to it will change back to 0, and then it will become go to 0 again this way. So if these forces are equal, for example, if this is 10 kilonewton and this is also 10 kilonewton, then we will see something like this, minus 10 kilonewton. All right, this is what happens. Yeah, that's right. So it will shear somewhere between, if this shearing ever happens, it will happen anywhere in this region. If I can highlight it, somewhere in this region, it will happen somewhere in this region, but it can never happen along this line. Shearing will never happen just along this line of action of any of these forces. It will happen somewhere in between them. So shearing can never take place along the line of action of the force. It will happen somewhere in between these two. So shearing is related to some sliding. Sliding can happen not along the line of action of the force. All right, you can think of it like, जैसे आप उसको काटते हैं ना, कागज़ से आप काटते हैं कागज़ को, अगर इस तरह का कागज़ पड़ा हुआ है ना और आप कैंची से उसको काटना चाहें, ठीक है, मैं उसको कैसे बनाऊंगा मुझे नहीं आ रहा, ठीक है, something like this, ठीक है, ये कैंची है, अगर आप इसको समझ सकें ये कैंची है, तो वो खैर ये तो कोई इतनी अच्छी डेमोन्स्ट्रेशन तो नहीं, जब आप कैंची इसके ऊपर रखते हैं तो वो एक साइड इधर आएगी, दूसरी साइड इधर आएगी, उनके बीच में डिस्टेंस बहुत मिनिमम रखा जाता है ताकि वो बेंड ना हो, मोमेंट ना प्रोड्यूस हो, रोटेशन ना हो, बस वो स्लाइड करे, कागज़ को काटना हो या किसी चीज़ को काटना हो। अगर आपने अंदाज़ा किया हो कि अगर आप इसके ऊपर जो कैंची है वो इस तरह से रखें कि एक साइड इधर काट रही हो, दूसरी इधर काट रही हो, तो वो बीच में बेंड होके वो फिर काट नहीं पाता, वो रोटेशन हो जाती है। तो आप उसको शेयर करना चाह रहे होते तो आप इसको एक इधर से काटते हैं, एक इधर से काटते हैं, तो वो बीच में जो है ना यहाँ से कट जाता है। तो शेयरिंग हमेशा फोर्सेस के बीच में होती है, ठीक, स्लाइडिंग उन्होंने करनी होती है ना, सो वहाँ पे शेयरिंग कभी होती ही नहीं है, तो वहाँ पे इनफैक्ट एक डिसकंटिन्यूटी हम आती है शेयर फोर्स के अंदर, एक जंप आता है, ठीक है। सो therefore this 3 meter is not included in any of these equations. At 3 meter the equations for shear is discontinuous. If our moment it is continuous, but for shear it is discontinuous. Now the next point is how to draw these bending, how to draw these equations, how to plot these equations. Let me take these equations to maybe just one where I can see them together, maybe somewhere over here. This was equation for bending moment, and this was the equation for shear. All right, and these equations are valid for values of x between 0 and 3 meters. And then next we have mx from here and vx from here. And these are valid for 3 meter and between 3 meter and 6 meter. Alright, now we need to plot these equations. Alright, we need to plot these equations. So you will, if you're using a computer, you can use Excel or anything else you can like. So I will use Excel and will plot these equations. So SFD and BMD. Okay, by using equations. Okay, so let's say this is X, this is V in kilonewton. This is how you should be also doing it, ठीक, आपने भी इस तरह से करना है, M in kilonewton, sorry, M in kilonewton meters.